So this was that we introduced linear transformation. Linear transformation means the vector space homomorphism. But when we say linear transformation, then product that means the composition of two mappings is also defined. And then the set of all linear transformations we call AFV. We proved that this is an associative algebra with identity over F. We proved one very important result which can be thought of as an analog of the famous theorem in group theory, namely the Cayley theorem. Cayley theorem said in group theory that every group is isomorphic to a subgroup of the group of all automorphisms. So here this becomes AF, and we proved that if A is an algebra with identity over F, of course here we always will mean. So if A is an associative algebra with identity over F, then is isomorphic onto a subalgebra of AFV for some vector space V over F. And we proved that A itself can be taken as V. AFV is therefore called the general linear algebra because every algebra is isomorphically sitting inside this general linear algebra. And in case this is finite dimensional, we proved that every element is algebraic over F. Algebraic over F means it satisfies a non-trivial polynomial over the field F. We proved, in fact, if the dimension of A is n, then the degree any element of A will satisfy will not exceed n. In particular, if V is a finite dimensional vector space, say of dimension n, then every linear transformation T of V over F satisfies a polynomial fx over F and whose degree will not exceed n square. Such a polynomial will be satisfied. In fact, this degree of fx will not exceed n, and when we prove this, that means we have proved the Cayley-Hamilton theorem for linear transformations. So this is what we did. Cayley-Hamilton theorem will take some time, but before that we have many other interesting results that can be obtained just by using the fact that every linear transformation over a finite dimensional vector space satisfies a polynomial. Minimal polynomial means a polynomial of lowest degree satisfied by P. We can also use this observation to decide about the linear transformation being regular or singular. Regular means it is invertible, singular means it is not regular. That means not invertible. So we define it. All right. So first of all, the minimal polynomial. So minimal polynomial. So let us take V over F be a finite dimensional vector space. So dimension of V over F, the vector space be finite. And P T be a linear transformation, that means this is an element of AFP. Then T satisfies a polynomial, let us say fx in f. That means when you replace x by t, then ft will be 0. That is, if fx is say a naught. Now a naught and a naught e, where e is the identity element, will be denoted by a naught itself. A1 x, an x, n. If n is the dimension. Then f of t will mean here, so if you say e, then e will be replaced by identity. So a naught I plus a1 t plus a2 t square and so on, a n t power n. Where t square will mean t operated on t and t power n means t operated on t power n minus 1 effectively. Now this is 0. This is 0 means this is the linear transformation 0. That sends every element to 0. Where 0 is the linear transformation, that sends every element to 0. So that means V under 0 is 0 for every V in V. So we know that this if the dimension is m, in that case the degree of fx will not exceed m square. So if there is a polynomial satisfied by t, then ft is 0, and this is the meaning of ft. Now this is said to be minimal. The polynomial or rather a polynomial fx in fx satisfied by t such that f of t is 0 is said to be a minimal polynomial of t if there is a polynomial say gx in fx satisfied by t, then fx should divide gx. We say fx divides gx. We say fx divides gx in fx if there exists a polynomial hx in fx such that this gx is equal to fx into hx. So whenever there is any polynomial that is satisfied by t, then fx should divide every such polynomial. Then we say this is minimal polynomial. Now any scalar multiple of minimal polynomial will also be a minimal polynomial. Therefore, if you divide by the coefficient of the highest power, in that case, the polynomial will become monic. Monic polynomial means the last term, instead of an xn, it will be simply xn. And that will be unique. We say a linear transformation to have a right inverse. If there is a linear transformation, say S, such that Ts is identity. So inverse invertible linear transformation. So let us say T be a linear transformation over the vector space V over F is said to be right invertible if there exists a linear transformation, say S, such that Ts. Now Ts is of course a linear transformation that we know already in AFV. Now this is identity, where I means identity linear transformation. Similarly is called left invertible. If there exists a linear transformation, say U here in AFV, such that UT is identity. Now this identity is in AFV is unique, that we know, and is called invertible. Finally, T is said to be invertible if it is both right as well as left invertible. That means there exists a linear transformation S such that your Ts is equal to St is also equal to identity. And in that case, S is unique. Is called inverse of T and will be denoted by this, the symbol T inverse. Now, invertible linear transformations are also called regular transformations. Invertible linear transformations are also called regular linear transformations. Now I leave for you to verify or find out at least one example that there are linear transformations which are invertible only from one side. That is left invertible but not right, or right invertible but not left invertible. Obviously, when it is invertible, the inverse, T inverse, is also a linear transformation. Is easy to see. So we have a small theorem now. So a theorem. So let V be a finite dimensional vector space over F. So let us take that the dimension of V over F be finite. In fact, we shall be considering most of the time finite dimensional linear vector spaces. Vector spaces are also called linear spaces. Then a linear transformation T means element of this here is invertible or regular, whatever you want to call. Any linear transformation which is not regular is called singular or not invertible. So the linear transformation T is invertible if and only if the constant term of the minimal polynomial is not zero. Is not zero. If and only. So let us take that Px be the minimal polynomial and its of degree, let us say k, and its constant term is not zero, then we shall prove that T is invertible. So let us say Px, this is A naught plus A1x, is AKX, K and Fx B. The minimal polynomial of degree k. That means AK is not zero for T. Then PT is zero. PT means A naught I plus A1T plus AK TK. You can take this to be monic if you want to use the word T. So, but I have not as such written specifically. And PT is zero. Now, two things we have to prove that if the constant term, that means A naught is not zero, then T is invertible. And secondly, if T is invertible, in that case, A naught is not zero. So first, if A naught is not 0. In that case, A naught inverse will exist in F. And what shall we get? This A naught I on one side, A naught I is equal to minus A1t minus A2t square minus AKTK. And this will make that this is identity. So A naught inverse exists, we can multiply. So this is a polynomial now here. So A naught inverse A1, this is the coefficient here, minus A naught inverse AKTK. Now this is same, you can call that this is T, and you can take here, say, for example, say Ft, and this is also Ft and T, where Ft is when you pull out this T from here. So this Ft is equal to, so when you pull out this, so this will be the coefficient minus A naught inverse A1 identity minus A naught inverse A2 T, and like this minus A naught inverse AK T power K minus 1. Minus A naught inverse AK T power K minus 1. So Ft is a linear transformation naturally. So Ft is the linear transformation here AFV, and this is what it is. So you can see that this commutes with T also, and what we get is that this is your inverse here. Now A naught is not 0. A naught inverse exists. AK is also not 0. So the coefficient here in Ft, T power K minus 1, is minus A naught inverse AK is also not 0, because we are in a field. So Ft is a polynomial of degree K minus 1, and it satisfies that it commutes with T, and also its product with T is identity. Therefore, what we get is T inverse is Ft, and degree of Ft is K minus 1. So the inverse exists. Not only inverse exists, it's a polynomial. And we know specifically also this polynomial, its coefficients, and the degree also of the inverse. Conversely, what we have to prove? If it is invertible, then the constant term must not be 0. So, conversely, suppose T is invertible, what we want to prove? That the constant term, that means A naught, is not 0. So suppose this is 0, then we want to see if there should be some contradiction. or something absurd conclusion. So let this be 0, let A naught be 0. If A naught is 0, then what will happen? PT will be, or PX. So PT is equal to 0, and this will be A naught is 0, so this is A1T, A2T square, AKTK. And this is same as T, here A1 identity, A2T, AK, T power K minus 1. Of course, T commutes with this also. Now this is 0. Also same as A1 identity, A2T, AK, T power K minus 1, T. Now T is invertible, so we can operate by T inverse on both sides. So we get that A1I plus A2T plus AKTK is 0. That means T satisfies a polynomial, and this polynomial is what? Gx, A1, A2x, AKX, K. This is K minus 1. K minus 1 of degree K minus 1. But then this is a contradiction. To the minimality of Px, because the degree of Px, the minimal polynomial, is K. So there cannot be a polynomial satisfied by T of lesser degree. And therefore what we assumed is wrong. And therefore A naught must not be 0. So hence A naught should not be 0. So we have proved the converse, that if P is invertible, in that case it should be, the constant term should not be 0. So what we have proved is that P is invertible if and only if the constant term in its minimal polynomial is not 0. There are equivalent conditions for a linear transformation to be regular or singular, but I leave for you to prove them. So you can prove first of all that if this is invertible, then T inverse, of course, we know is a polynomial, and its degree also we know is 1 less. Likewise, you can also prove that if the dimension of say vector space V is finite, then the linear transformation S is singular if and only if, let me state also. So we can prove here that let us say the dimension of V over F be finite, then a linear transformation say T over F is singular, as we had seen for regular if and only if condition. Now is singular. The advantage of if and only if is that it is a complete characterization. So this is singular if and only if there exists a linear transformation say S AFV such that S is not zero, or you can include that here itself. So such that TS and ST are equal and equal to the zero linear transformation. The proof is easy. Since we have proved that a linear transformation is regular if and only if the constant term is not zero. That means it's singular if and only if the constant term is zero. So if it is singular, then minimal polynomial will have its constant term 0. And naturally, just as we have seen here, there will be a polynomial st, ts is 0, and s is not 0. And what was that polynomial? S that we can write is once a naught is 0, then this is a1 identity, a to t plus and so on plus ak t power k minus 1. Since ak is not 0, so this polynomial is also non-zero. And of course, its degree is lesser than the degree of the minimal polynomial. Likewise, for a finite dimensional vector space, you can also prove that this is right invertible, then it is invertible. That means only one-sided inverse is enough. So a linear transformation is regular if and only if it is one-sided invertible. That also you can prove. And also you can prove that this is if and only if there exists a vector, say non-zero vector say v in V such that Vt is 0. Now, is follows from the statement. This is that the singular if and only if there is S, non-zero S, such that St is equal to Ts is equal to 0. So if there is a non-zero linear transformation, that means there is some vector. So for this, here you can see that T is singular from the above statement. So T is singular. So it implies there exists a non-zero S in AFV such that this St is equal to Ts is equal to 0. Non-zero S means what? So there exists a vector, say, W. So there exists a W in V such that Ws is not 0. And you can take this as this vector V. So this makes that St is equal to 0. So this is W S T is not 0. So put V to be WS. V to WS. Now this WS this is not 0. And the VT is 0. So this from the statement above. In fact, these two conditions are equivalent. So there are various conditions that are equivalent for a linear transformation to be regular or not regular, that means singular. Now we can prove one more condition which is also equivalent, that a linear transformation is regular or invertible if and only if it is onto map. We can also prove that this is also if and only if T is 1 to 1. Onto means for every element in V, there is an element, say U in V, such that UT is equal to V. So what we define as the range here, range of T. So range of T is basically the set of all vectors of the form Vt, and V comes from this. You can see is also a subspace of the vector space V, and T is set to be onto therefore if the range of T is same as V itself, and the dimension of this subspace RT is called the rank of this, and the dimension of the range is called the rank of. Likewise, we have the kernel. If you remember, kernel of T is the set of all vectors V in V such that Vt is 0. This is a subspace of V, and the dimension of the kernel of T F is called nullity. Kernel is also called null space, and the dimension of null space is called nullity. We shall prove that in case of finite dimensional vector spaces, that rank plus the nullity of the linear transformation T is equal to the dimension of the vector space. And this is famous theorem due to Sylvester that says that rank, or is also known as rank nullity here. So one theorem that you can prove is also interesting. So this theorem says that for a finite dimensional vector space, the dimension of P over F be finite, then, and let us take T here. And T a linear transformation. Then T is regular. Regular means invertible. If and only if T is onto. T is onto means V onto V. is also equivalent to if and only if T is 1 to 1. V1. V1 to V, or T is 1 to 1, V2. So quickly you can see the proof for one I do, together you can prove yourself. So if T is regular, let us say T is regular. Now T is regular means T inverse exists. That is, there exists a T inverse, the linear transformation of inverse of this, such that what is the property of this? So T inverse is same as T inverse T, same as the identity map. That means every vector under this, so V is equal to Vi is equal to V T inverse T is Vt inverse under T. So this is V. So you can call this as U. So we have, so U equal to Vt inverse is in V, such that Ut is V. That is for every such vector. There is a U. So what we get for V? This means T is on 2. That means T is. Conversely, suppose T is on 2. What we want to prove? It is on 2. T is regular. This is equivalent to proving that if T is not on 2, then T is not regular. That means T is similar. Okay. So what we want to prove that T is not regular, then T is similar. And proving T similar means there exists a vector such that this vector is not 0, just now I stated, but its image is 0. Okay, so suppose T is singular. We must show that other T is not regular. T is not regular, then this is not on. This is equivalent to prove that if T is not regular, then this is not on. sorry, T is not regular, then T is not on. So suppose here now, if T is not regular, then there exists a vector which is not 0 in V1, call it V1, such that V1T is 0. Okay. Now V is a finite dimensional vector space. V1 is not 0. So we can blow this up and add vectors if required, so that we get a basis which has V1 as its one of its elements. So we can find out a basis for V over F of the form. So this will be V1, V2, and say Vn, where dimension of V over F is n. All right. But then V1T, V2T, Vnt, this set now is a subset of the range of T, and the number of non-zero vectors here, because since V1T is this, since V1T is 0, the then number of non-zero vectors in this set are less or equal to n minus 1. Now since these are the images of the basis vectors, so the dimension of the range space will not exceed the cardinality of this set, and that is n minus 1. But then the dimension of the range of T over F will not exceed n minus 1. Now n minus 1 is strictly less than n, and that forces T is not on. So we have proved that if T is not regular, then T is not onto. That means T is onto, and in that case, this should be regular. So this is also if and only if. Finally, I just would like to state a few observations from here, and I leave for you to prove that about the rank. So if S and T are linear transformations, then the rank of the product is, you can prove that the rank of the linear transformation here as T is less or equal to the minimum of the rank of S and the rank of T. And in case S is regular, then you can also see that the rank of T and its conjugate are conjugates here are called similar. If T is regular, in that case the rank of T is same as rank of STS inverse, same as of course the rank of S inverse PS for every invertible. For every invertible, invertible T मान लिया ना already. So this T inverse TS TS T inverse for every S in E. So we shall wind up here and would look for something. The linear transformations in the next class. So thank you very much for your kind attention. We wind up here.
Thank you, sir.